a very quick update to the plan of the semester. The course project, I think, is not really feasible that you guys can finish all the layouts. Especially, I really want to assign you some cadence labs towards the end of the semester. So we are not going to lay it out in electrical VLSI for the entire ADC. It's impossible to get it done by the end of the semester. It's too much. However, we still have to run the simulations under C5, which is 5 volts VDD for the power supply, because the example, if you click the course project link, get into the web page, the instruction, you'll see that I have a few references over here, and one of them is from Ultra Vanill's summer project. And also there are some old SAR ADC files, and I believe if you directly open them up in lec35, it can show this result directly, so it's done, right? But you are making some changes to it. First, you have to modify, change the transistors and use the C5 models instead of the whatever being used over here. I think it's 50 nanometer technology, 1 volts. And second, it has to be in electrical VLSI, and hopefully next time, next year, students will be able to start from what you have done and start building the layouts in electrical VLSI. So the timeline. So project part 1, I don't know if I've started working on this or not, but I think on Monday I said we should start working on the sequencer and code register and finish it by the end of this week, if that's still doable. So it's basically just 16 or 17 D flip-flops. And just don't make mistake when you build the first D flip-flop, then just replicate it to build a circuit like this. This one. Okay. And again, the buffer is not required, I think. We can tell the difference. If you have the buffer in there, or if you don't have the buffer in there, it's just the two inverters in series. Okay. It may work if you don't have the buffer. It's just you just don't run the frequency too high. Okay.
So we don't need to do the layout.
Don't. C5 simulation in electrical VLSI.
Okay.
Mm-hmm.
That's just the normal simulation.
Yeah, just show yeah, there are a lot of other things that we can do, but I don't think we want to spend that much time. Just show the sine wave. You can recover the sine wave, then that's it, right? Run it slow and see if you can see a thing like this, and then increase the clock frequency so you can, overlap the analog input. If you zoom in, you can see the V in is actually over there, right? Mm-hmm. Really trying to follow that input, and this one takes pretty long time. I think it runs for 30 minutes or so, just for one period of sine wave in LT-SPICE. But electric VLSI is also pulling LT-SPICE for simulation, so it's going to be the same amount of time. Okay. And if you zoom in, you can see all these little discrete signals trying to follow the V-in. Right. I think I haven't covered a few other things, but let's look at the timeline first before we move forward. So sequencer, code register, you are wondering what they are. I think in the ADC lectures, you'll see a lot of details in there regarding why we need a sequencer and code register for the SAR algorithm. Where they are. So we did it pretty early in the semester. Okay, here. Okay, ADC, basics, comparator, SAR algorithm, and the SAR logic. I think this is where we cover the details of the sequencer and the code register. Okay. Here, more about star logic. Okay, so that's the code register, which is the ones at the bottom. And the sequencer is on the top, is the top part of it. So the sequencer is just shifting that one to the right each time, okay? So it's outputting a 1, 0, 0, 0, 0, and then shifted 1 to the right. So it's giving 0, 1, 0, 0, 0, like that, okay? So that's a sequencer. And the code register is the one at the bottom, which receives all the bits from the sequencer from the top to set each of them in a certain order, okay, in order to register your comparator's output. So it's actually pumping or injecting that comparator's output in here. Why do we need the comparator's output to be registered in all the D flip-flops? Why do we need the comparator's output? See? So if you look at the table, the final result of the star block is just A0, A1, A2, A3, and these are the comparator's output. If you go through that star algorithm again, you can find out it's basically the comparator's output that forms the ADC's output eventually. So you just need to put them in a certain order, like the first one has to be the MSB. So if you forgot how that works, go back to remember all the circles for the cycles we did in the midterm exam as well, right? So for the cycle, if you have 4 bits or 5 cycles, right? How many bits do we have for the ADC to finish the conversion in 5 cycles? 4, right? So it's 4 bits from D0 to D3. The cycle 1, you have to reset everything, or you have to set the first bit and reset everything else. So in the little circle, right? Remember, we have to start with 1, 0, 0, 0, right? Which is exactly 50% of the entire range. So this is where we get started. That's a star algorithm. We start with 1, 0, 0, 0, right? And the second cycle, we got a comparator's output, and we insert that output to the MSB, and we shift all the bits to the right by 1 bit. So that's the original one is at D2 now, right? And the next cycle, we plug A2 in here, and we shift all the rest of the bits to the right by 1 bit, right? So the 1 is now here, okay? And then we plug in A1 to here and shift 1, 0 to the right, so I have 1 left. So I have to do it one more time. The comparator's output give us A0, so we plug A0 in here, so 1 will be shifted out. So eventually the final output is actually the comparator's output being reordered in a certain way, okay? So that's why here's a comparator's output, and we're registering that thing into the D flip-flops each time. Remember the when we have a 1 here, because we're on the top, we have a sequencer, so the sequencer will shift the 1 to here in the next cycle, and this one will set this D flip-flop and give a rising edge or give a 1 to the Q, and that Q is being used as a clock for the previous stage, so it's giving a rising edge to the clock. Okay, and the rising edge of the clock is going to trigger that D flip-flop function, so the comparator's output here, whatever it is at the moment, will be registered into Q and becomes A3, right? In the next cycle, that one will be shifted to the right, so this one will be, so this one, where is this bit connected to? Where this one is connected to? The sequencer's output, connect to where? To the code register. So imagine you have a sequence on the top, right? Same number of D flip-flop on the top, and it has all the output, connect to the code register. So that line, right? That line, or the it can be a bus, right? Because you have 5 wires in the bundle. So these are shorted to where? The sequencer's output are shorted to where? Which is basically these lines, right? They are shorted to where of the code register, which is this guy. No. Set. So D is shorted to where? For example, the MSBs D is shorted to where? Comparator's output. Okay, it's not just the MSB's D, it's every single one is shorted to the comparator's output. Okay, and the sequencer's output on the top are shorted to the set. When you are moving or shifting that one to the right each time, you are citing each D flip-flop each time. Okay, so now here's the problem. If you look at the table, we plug in the comparator's output only to one place. For example, for A3, we only plug this bit in here, but not the rest of the digits of the code register. However, the comparator's output is shorted to all the Ds. Does that make sense? Is that going to work? If it's shorted to all the Ds, why not it's registering the comparator's output everywhere? Like you're not getting like A3 for all the digits, but only one. Only the MSB, why? Why it's not being registered to the rest of the D flip-flops in the code register, but only the one we want, the one we need. No, Q, you cannot force Q to 0, could you? So you didn't do anything for reset. Reset is at the bottom, I didn't draw it. But I didn't connect reset to anywhere. Why? Why the comparator, this comparator's output here, right? It's just one wire, it's shorted to all the Ds. So why each time, see here, we desire that each time is being registered to a certain D flip-flop, not all of them, right? You need the rising edge to pass it. So do you have a rising edge for all of them? Q makes a rising edge. Why Q makes a rising edge? Why Q give a rising edge to that certain D flip-flop? So to have a rising edge, you register it, right? That's how the D flip-flop works.
What makes you have a rising?
Yes. Clock switch from 0 to 1, that's Q, right? That's Q, how Q works. Q switch from 0 to 1, that's why it gives clock from 0 to 1, then triggers the previous D flip-flop to register it here. You set it from where? From the sequencer on the top, right?
Oh, the top part.
Yeah. No, this is code register, right? Yeah, this is on the top is the sequencer. Sequencer's over here on the top, right? Puts a 1, right? To set it, right? To set each D flip-flop each time. That's how it gives a Q a rising edge, and that's how it gives a rising edge to the clock of the previous stage of the D flip-flop in the code register. That's how it's only registering a comparator's output to one of them. Okay. All right, it's been 2 months. Understandable. Yeah, you guys already went through everything here 2 months ago, and it worked. But yep. All right, so now it makes sense, right? Now let's, oh, another thing. How do we, so this is the desired output. We need a 1, 0, 0, 0, and then shift the 1 to the right, and then shift the 1 to the right, keep moving. So this is the desired output. We need to design the circuit to make it happen. That's how it works in digital world. And we need a circuit to do this, to implement this, okay? And here's a circuit, which is called a sequencer, right? And we have to short the first D's input to 0 or to ground in order to make it happen, because so at the very beginning, when you get an initial state like 1 and all zeros like this, you need to set the first one. See, here's the set, the first one, and reset the following ones. Excuse me. Is that correct? If you look at the output, the first one is outputting a 1, and all the rest are outputting zeros. Right? Definitely, you are setting the first one, resetting the following ones. So in that case, you just need a 1 input. You don't want to do multiple ones. It's just digital signal, doesn't matter. Doesn't matter the last name of it. So the name of this one is 1 reset, right? So 1 connect to, it's called reset, but it's shorter to set. So actually you are setting the first one. And after that, you have to change it to 0. You have to change it to 0. That signal, have to change it to 0. When you change it to 0, none of these set or reset are active anymore. And so all the D flip-flops are being operated under the D flip-flop function instead of, or the D flip-flop mode instead of the set and reset mode. So you can start registering, or you can start shifting all the bits to the right. But I have to keep the first one to be 0. Right? One more question. If you have the first one to the D, if D is 0 here, if D is 0, all right, and if you set it, are you getting a 1 or getting a 0 here? If you have a clock still always running. If you set it, get a 1. Doesn't matter what the D is, right? Yeah. All right, so it's good to know the circuits of the D flip-flop instead of just learning how it works, right? You know what's happening inside the circuit, inside the block. Okay. That's a sequencer and code register. Is that reasonable to have it due on Friday? Okay, simulation. So you need to show an 8-bit sequencer and code register. You just need to build one of them, and I recommend that you use TIs. Where's the TIs? All the 9 gates are the ones you went through in the class on Monday. This one, right? Just use this one. But I have to change it to 5 volts. I think the size of the transistors doesn't matter that much. 4 to 2 works. 10 to 2 also works. Just the logic. I'm saying 10 to 2 times of lambda, right? Because C5, 1 lambda is 300 nanometers, right? So 2 lambda is 600 nanometers. So why do we want to use 2 lambda instead of 2.5 lambda? We always use integers, right, for multiples of lambda. So why do we want a 2 times lambda instead of one time of lambda? Yeah. Yeah. So smallest is what? Smallest feature is allowed for that technology is what? No, it's called C5, right? C5 is 500 nanometers. So it's 500 nanometer or zero 0.5 micron is the smallest node it is able to fabricate on the chip. Mm. And 2 lambda will be 600 nanometers. If you just use 500 nanometers, I believe it's fine, but it's probably getting a lot of maybe lower yield for your chips. So usually we use 2 lambda, which is a little bit larger than the smallest allowed feature on the chip. So 2 lambda can be the smallest length, right? You can keep using that length. If you want to make it stronger, you just increase the width. So you can start from 2 lambda and 4 lambda, 10 lambda, depends on the frequency of the circuit, right? If you feel like it's struggling driving the load or driving the rest of the circuit, you can increase the width a little bit. 2 to 10 works. 2 to 10 works. And so in your simulation, I'm going to show this, right? First, I have to generate a fake comparator's output. So imagine you have a circuit like this. Okay, set and reset. It could be have a reset. It's just a one line, right? Remember we connected reset to set for the sequencer. The first one, you see the reset is over here, right? Reset is over here. It's called reset. It's the name of the line, but it's actually connected to set for the first one, for the sequencer. And for the rest of the D flip-flop in the sequencer, I connected that signal to reset. Okay, is this 1 active or 0 active? 1 active. Which D flip-flop did I use? Oh, where's? Yeah, 0 active. So I'm talking about the sequencer circuit, right? On paper, I assume it's 1 active, but now if you look at the circuit hardware, it's actually 0 active. So I actually need a 0 to set or reset it. If you look at the simulation, did I set or reset it? So I do. Okay, so that's the reset. Whenever reset is 1, all the D flip-flops in the sequencer are being operated in which mode? Which mode? If the reset pin is 1, if reset is 1, if reset is 1, okay, reset is 1. Which mode are these D flip-flops are being operated in? If reset is 1. If I put a 1 here, is this am I exciting it or resetting, or is it a D flip-flop? No, if I give a 1. Yeah, 0 active. So it's not doing anything, right? Remember the D flip-flop? They're NAND gates. So NAND gates, you give a 1 to it, it doesn't do anything, right? So these are the TI's D flip-flop with the NAND gates in there. So if you give a 1, it's actually not doing anything. They are perfectly just D flip-flops, registers. Okay, if I put a 0 here, if I put a 0 here, so 0 here, right? If I put a 0 here, they are shorted together, so I have a 0 here for the reset, okay? And they are 0 active, okay? So count how many D flip-flops do I have in the sequencer. How many D flip-flops are in there in the sequence? 9, okay? So 9 sequencers. And the 9 sequencers, if you combine them as one binary number, okay? So what is that binary number? If I reset everything, what is that binary number in decimal? No. If I give this pin, right? So reset here, right? Reset is shorted to all. So this pin is shorted to all the reset for the other ones, right? But this code is called reset, but it's actually shorted to set. Okay. If I give a 0 to this node, they're all shorted together. So if I give a 0 to this node, what is the output? If it's a one binary number, what is the output at the sequencer? It's a 9-bit binary number. So what is that? What is the output in decimal?
Yeah.
Which one? What is that? 256, yeah, 2 to the 8th, right? What is 2 to the 9th? 2 to the 10th? All right, so we got 1 here, but all the rest are zeros, right? Okay, so that one, when flip, okay, so because they are 0 active, so when you have a 1 here, you actually don't want to use it. Because 1 is not going to treat the set of the code registers D flip-flop. So I have to use a Q bar here, right? Make sense? Okay, I have to use a Q bar instead of Q. Okay, just use a Q bars for all of them. And it's going to shift. So instead of shifting 1, it's actually shifting a 0 to the right in the code register. Does that make sense? You have all the have a lot of 1s, but only 1 0 is being shifted to the right here for the lines, right? So whenever you shift a 0, for example, I shift a 0 here. The 0 was here and shifted to here now. Okay, what's going to happen? What's the output here? If I put a 0 here, what's the output here? 1. So it's connected to the clock. So rising edge, right? Rising edge is going to trigger. It's going to register what where. This to here, right? Make sense? Okay. Okay. So you need to show the simulation. First, I have to, since we don't have a comparator, we don't have an op-amp, so you just have to create a fake comparator sequence. For example, that's a comparator's output, just a square wave. Your D flip-flop, your clock is the rising edge is sampling the data in the comparator's output, the comparator's square wave. So samples here got a 1, samples here you got a 1, samples here got a 0, samples here got a 1, samples here got a 0, so on and so forth. And eventually it registered these numbers into your code register. Okay, and you need to display all the output of the code register starting from MSB. It's bit 0 to bit 7, so I have 8 bits. So when you reset it, okay, at the very beginning, you put a 0 here, okay. When you put a 0, it's a 0 active. So when you put a 0 here, it's actually giving 1 and all zeros for the output. If you look at the output here, it's definitely 1, right? 1 here for the final output, and all zeros. Okay. So that's the first data I will have. Oh, actually here, 1 and all zeros. And the next, it's gonna shift that 1, the initial 1, to the right, okay, and plug in A7 to it. So A7 is a first comparator's code. It's being registered into the MSB of the code register. Okay, so if this is A7, what is this? What is this number? If this is A7, okay, let me ask 2 questions, okay? If this is A7, what is this? And what is this? What is this? What is this? This is the original 1, right? The original 1 getting shifted to here. Let's take a look at the table first. Make sure you guys are getting it. Wait. Things on top. Okay, so it's not on top. It's crazy. Sorry about that. Oh, it's in the notes. That's why. Let's go back. This one. Okay. If this is A3, is it going to change over time? No, it's going to be A3 all the time. It's just plugging the new comparator's output to the after that. Okay, so that's going to be A2 here. That's A1. It's A0. Eventually, it becomes A3, A2, A1, A0. So if you come back to the waveform, All right. So these are output 7, output 6, 5, 4. Okay, and this is the initial one. Okay, and what is this one called? A what? You are looking vertically, right? What is this one called? A7. You have 8 bits. This is A7. What is this one? A6. What is this one? A5. What is this one? Wait, A5? Why? So are looking from left to right. Don't do that. We are looking vertically, right? Output 7, so how we get this waveform? I probe it. So I probe that certain output. That's always the MSB of the code register. It's always from that location. Okay, so you register it over there, and it performs like a memory. It stores that bit all the time. If you look at the table, it's not changing. A3 is always A3. A3, A2, A1, A0. Whenever you get all the A's, the final result, you combine them together, that's the final output. Okay, so what is this A? One more time. This, 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 this. 4, 3, 2, 1, and A0. So what is the final output, final result? These ones or these ones? Which one is the final result? These ones or these ones? Which one is the final result? The box, yeah, vertically, look vertically, like these ones is the final result. Because each bit or each line represents a bit in the 8-bit output. Is that clear? Where's the initial one eventually? It's gone, yeah, being shifted out. So where is it? Here, right? It's just gone. It's being replaced by a 0. Okay, and we don't care where that goes. It was being stored in the parasitic capacitors in the circuit. But when it's getting replaced, it could be either discharged or charged. It could be discharged if you're getting a 0 to replace a 1, right? If you got a 1, yeah, we don't care about that one, actually. Okay. Is that clear on how to simulate this guy? Could you do it on by Friday? And so upload it as a report to show the simulation results, like what I did over here, similar results on the website. Okay, you can, add a link to the all the lab reports. So before the beginning of the class on Friday, let's get it done. Okay. All right. Another thing, sample and hold. It's a super simple circuit to build. We have gone through this for many times. Okay, we're not doing the layout. Then I worry about the capacitor. How do I lay out the capacitor? How do I isolate the P NWL or PWL for this guy? PWL? What is a PWL in C5? PWL is a P substrate, right? You don't really have a PWL. So the NWL is the PMOS or NMOS? PMOS, okay? PMOS is in the NWL. And we should short, so what is this line? For the schematic, it's pretty simple. I just short it here. I don't even need to care about the physical device, right? Since you guys are well educated, you know what's going on. You'll get hired in the company when they are asking the questions about the device, you should know the details about it, So for the layout, what's really happening in the physical world? What is this? The body, yeah. So what is the name of the device? Yeah, so what's the name of the tab? No. What's the name of the tab? It's typing what? Yeah, so it's typing NWL, right? So what's the body of the PMOS? Let's start from here. NWL, okay? So what's the name of the tab? NTAP. Okay, so that little line here in the physical device is an NTAP. It's a little wood plus material in which well. So it's being shorted to where? Source. Yeah. Yeah, you can see from the schematic it's connected to the source. Why the source has the highest potential in the circuit? What? Oh, so the capacitor stores a floating VDD, remember? Okay, it's getting charged up by this guy, and it is able to pass the entire VDD to the cap because we have a higher gate voltage. So the PMOS or NMOS? NMOS. Good. I'm so glad I didn't jump in the trap. So happy. So you guys got it. Okay, cool. So that's the NMOS, and you have a higher voltage of the gate voltage, so you can open it up wider or more, right? So you can pass the entire VDD to the cap. So whenever you turn on this, so it's like a valve. You think about that. This is a water source, and this is a bucket. You know, in the I don't know how many years ago, maybe 50, 60 years old, 60 years ago, they have a big water tank on the top, hanging on the wall in the restroom to flush the toilet, right? So you turn on the valve. So this is like a valve, right? You turn it on, it starts flushing the toilet. Okay, so when you turn on the NMOS, it's just like a switch or valve of the pipe. You turn it on, it starts discharging the bucket, and it pulls water from the water source on the top and charge it up. So that's the source, right? Originally, you do have some charges, but when you turn it on, it will all be dissipated to the ground. So, but it charges up the cap. When you close it, it's gonna float. It's gonna store a floating VDD. Okay, so the bucket will be full because this will be on as well. So it's actually charging up the bucket, and also you are but you have to turn it on in order to give a pressure, so it is able to charge it up. But whenever you turn it off, this becomes a isolated water source. Okay, it's just a bucket. It doesn't have any water source anymore. It's a floating. It stores a finite amount of charges in the bucket, which makes sense, right? But it's a floating VDD. And whenever the voltage in comes, which is a sine wave, it goes up. So you are adding a little voltage. You're putting the VDD here plus minus, and plus minus the V in as well. So it's basically two batteries in series. So you're adding that V in into the. I think I did this last time. So I have a floating VDD here, and there are a few circuits, but eventually it's making a connection to it, and that's V in, which is the sine wave. V in. So when we talk about V in, it's comparing to ground, right? If you probe it, you got a V in, or plot it in the oscilloscope. So V in will be shorted to this line. If you look at the two batteries, is plus minus plus minus. If you probe here, because the oscilloscope has a ground line as well, and you probe here, you are getting actually VDD plus V in. They are being superimposed on top of each other. But the voltage difference between the capacitor is not changing, still VDD. Okay. However, this makes a lot of sense because you do need this voltage to be fed into the gate voltage of the transistor, the gate, right? So this voltage becomes VDD plus V in, and the voltage here is V in. I know V in changes; it's a time varying signal. So this is VG, this is VS. So VG minus VS becomes VGS, which is exactly VDD. So it's not changing. You are getting a constant VGS. If you get a constant VGS, the channel resistance is not changing. Okay, so your signal output here is not getting distorted. That's a key point. That's the whole point of this circuit. And I also want to show you guys that why this happens. If you look at the simulation, if you build a circuit in LD-Spice or in Electro VLSI, you'll see exactly the same simulation result. So that's a V in, right? That's an AC signal. It can be anything, can be a sine wave, can be anything else. All right. However, the output, or VG, this is VG, okay? You can see VG is changing and having the same shape as the V in. And the difference between V in and VG is constantly VDD. You're having a discrete signal because it's being clocked, and during the clock cycle here, it's being reset, so it's discharging all the charges over there. But however, whenever it's working, right? Whenever it's working, you are having a constant VDD as VGS. That's the goal, okay? Works, so everyone is happy. So we're not getting the signal distorted. So you want to show that for the sample and hold circuit output, and simulate it and shows that it's getting sampled. So I zoomed in at one of the sampled point, and you can see it's getting sampled. So for this diagram, which point is being sampled over here? Which voltage is being sampled? Here or here or here? Which one is being sampled? Mm-hmm. Which one is eventually being sampled, being used? This voltage, or this voltage? Which one is being used for the ADC conversion? Yeah, here, right? Because it's being held here for a certain amount of time. So you got enough time here for the conversions, right? So if you have eight bits in the ADC, how many cycles do you need to finish the conversion? How many cycles? 8-bit, yeah. You need 9 cycles, right? So it takes time. Okay. And now, based on the frequency of the sample and hold, you can see there's a little time delay here, okay, which is okay. You have a lot of things in the sample and hold circuit. So I'm trying to create a pulse, right, for the sample and hold circuit. Do I need this pulse to be 50% duty cycle? What does that mean? 50% duty cycle is on time is 50% of the entire period, which is a standard square wave. Okay, you can see this sequence for the blue line here. The clock it's definitely not 50%. Okay, it's probably like 10 to 20%. Do I need a 50% duty cycle to make it work? Why? Why do I have to get a 50% duty cycle? I mean, even for this, the width of the sample and hold pulse for this simulation, I'm wasting a lot of time here. Do I really need to track it? No, that's a limit, right? It has a little time delay to reach the full voltage, to reach the voltage here. I can even shrink the pulse width even more, probably to here. Okay, who cares? Still gonna work. I sampled it, there will be a time delay, it's okay, it reaches the full voltage, and then I just give it a little bit more room here, and then I start hold it. What's the benefit of doing that? What's the benefit of doing that? Can you shrink this time period further? Could be challenging because it takes time for the start block and everything in ADC to finish all the 9 cycles. Can you shrink here a little bit? Yes, you are wasting time here. Why do you have to track it? You don't have to track it. You sample it, you hold it. Why do you have to track it? It's tracking, right? So the right line is tracking it. Why is tracking it? Why it is able to track it? It's amazing, right? Even though I don't want it to track it. Why am I able to track it? Why the circuit can track the V in? Because this is a pass gate, right? Whenever it is on, whatever here will be passed to VL, right? It's just going through. Until I shut it off, it starts holding in the capacitor. Okay, so that's how that works. And you need to show that it's sampling, tracking, and holding. Okay, for the sample and hold circuit, which is due after the break. And for the comparator, just directly use whatever we have and change the size and VDD of it, or the model of it. And I think I provided another one, which is this one, okay? I believe because it's from Dr. Baker's textbook, that's examples including capacitors and op-amps and a lot of other things in the folder. You open it up, it's going to show all the design details in electrical VLSI because these were built in electrical VLSI. And I believe you can directly copy and paste from there and use these ones, one of the op-amps over there as the comparator. You can run the simulation first to verify it works. Okay, you give an input, you give one signal to one of the inputs of the comparator and oscillate the other one, see if it's comparing. Okay, and if you look at the final diagram, there's another thing I want to talk about. So if you look at diagram, now we know how to build the star block. This is what we talked about for the first half of the class. So it's just a sequencer and code register, right? So you have a sequencer and code register being wrapped in the box like this. And the comparator is one of the op-amps you can use from the folder. And sample and hold circuit is the one we just talked about. You put in the box. And so before you put them together, you have to simulate every single one individually to make sure it works. And then you put them together. And the R2R DAC, just resistor strings. We did a lot of these things at the beginning of the semester. We built a DAC using resistors in electrical VLSI. And this is a parallel in, parallel out D flip-flop. The reason we need that one is if you look at the table of the SAR Logic's output, we are updating the output each time. If you have 8 bits here, we need 9 cycles. So there are a lot of intermediate digits where outputs are not the ones we want. So eventually we are having a A7, A6 until A0. That's the final result. However, in between, before we finish all the 9 cycles, we have a lot of intermediate results. So we don't want to output them to the final output. So we need this parallel in, parallel out D flip-flop array is being used as like a door. It's a door register, right? So whenever it's ready, you kick them out. But before that, you wait. You know what I mean? You need to wait until the 9 cycles are finished. Then you just kick them out. And how to verify the output? You need another DAC. Because the door register is a parallel in, parallel out 8-bit D flip-flop. So it's a digital voltages. If you probe it in LTSpice, it's showing 1 zeros. So you cannot recover that. Sine wave. So I have to use another DAC to look at sine wave. And these are the signals, and this is the control logic. I think we can probably talk about it on Friday. We don't have to modify the control logic, but it may not be perfect. We'll talk about it later, right? It works in the simulation, but we haven't, verified all the quality of parameters of the ADC. For example, DNL, ANLs. No, DNL and geez, what's the other one? RNL, no. DNL, NLs. Thank you. All right. We'll take some time to do it. If we still have time, we'll try to analyze these parameters. But if you can recover the sine wave, I think you guys are done for the term, right? Okay, I'll see you guys on Friday.